Welcome back, Chemistry 30. This is the MS1.6 Molecular Shapes section. Here we'll look at describing some of the molecular shapes commonly encountered with molecules. So you should have done that molecular geometry lab and have seen how this comes together in a three-dimensional view as opposed to a two-dimensional view such as this carbon tetrachloride. So even though Lewis structures can be used to account for the formulas of covalent compounds, they do not indicate the shape, really. They simply show the number and type of bonds. For example, the Lewis structure of CCl4 tells us that we have carbon bonded to 4 Cl atoms. And of course, doing formal charges, we see that that is the correct structure. The Lewis structure is drawn with all the atoms in the same plane. So on this flat piece of paper, the actual arrangement, however, is the Cl atoms are at the corners of a tetrahedron shape, a geometric object with 4 corners and 4 faces, like in each an equilateral triangle. So it's a pyramid shape like this. So we have our corners. Can't see them behind there, but there's a face in behind here. If I was to draw this kind of see-through, maybe we could see it. There we go. So there's 4 faces. There's one here. There's one here. There's one behind here that we can't see, and there's one underneath here. So that's 4 equilateral triangles forms a tetra. Tetra meaning 4 hedron. So we can imagine as a ball and stick model, like we had in that lab that we did, or we could have a space filling model in which we have almost like balloons here, a central balloon plus the 4 other ones, etc. But it forms a tetrahedron. And you would have seen, of course, that the angles made here between here and here, this angle is 109.5, 109.5. 109.5 is that magical angle that makes that tetrahedron shape. The shape of a molecule is determined by its bond angles. So the angles made by the lines joining the nuclei of the atoms in the molecule. The bond angles of a molecule together with the bond lengths define the shape of that molecule. In the above figure, you would see that there are 6 Cl-C-Cl bonds, so C being in the middle, joined to the Cl's. There are 6 of them, 1, 2, 3, 4, 5, 6, and they make a number of 109.5. The angle size characteristic of a tetrahedron. In addition, all 4 bonds are the same length. They're single bonds. So, of course, we talked about this before. Single bonds tend to be longer than double or triple because there's only 1 electron pair there. And if you increase the number of electron pairs, they attract each other. You can think of it as almost electron glue holding it together. Thus, the shape and size of the CCl4 are completely described by stating the molecule as a tetrahedral type shape. So on the next page here, we can think of the molecules of having the general formula AX to the N, where A is the central atom and the X atoms are the ones that are bonded to it. So for example, AX2 could be the CO2 molecule, or AX2 could be an H2O molecule, where A is the central atom, O, and the H's are attached. And then if we look at AX3 type molecules, we could be looking at sulfur trioxide or the ammonia molecule and so on. And you would have seen the shapes that are made by doing that little lab. The number and of shapes possible for an AXN molecule depends on the value of N. Commonly, we're using 2 extra atoms bonded to a central one, or up to 6. And we'll look at that in more detail in the next section. So if we take a look here at some of these shapes, so if we have an AX2 type molecule, it could be this. It could make 180 degrees here. It could be a linear. Water, though, is not a linear molecule, as we'll see in the next section. AX3, one type, could be a trigonal planar, so 3 pieces here making a flat surface. So that's where we get the name planar. Here, AX4 could be that tetrahedral shape as we talked about. Trigonal bipyramidal could be an X to the 5. So we have, if you join these up, we see we have a pyramid on top and we have a pyramid on the bottom. So just like a bicycle has 2 wheels, bipyramidal has 2 pyramids. Trigonal, meaning the 3 atoms there. And then octahedral. So we have a pyramid with 4 faces on top, 4 faces on the bottom. So that's where the octa comes from. So these shapes are considered the stable shapes that these make, because what they do is they maximize the separation. You'll notice in that little activity that you did, when you twist a molecule around, it changes, but then it repulses the other atoms so that it's maximum separation from each other. That's considered the stable part of that molecule. So over here, with the use of formal charges, draw the most reasonable structure for each, and then state the shape. So it's just like what we've done before, except we're doing the additional part of stating the shape. So over here, if I look at CO2, which we have done multiple times before, of course, carbon is a group 4 atom, and oxygen is a group 6. So we'll have 4 plus 12, that'll give us 16 valence electrons. So of course, starting this out, use single bonds to start off with. 2, 4 I've used. Then put the remainders on the outside, like that. 2, 4, 6, 8, 10, 12, 14, 16. And of course, if we do the formal charge calculation, oxygen is group 6, carbon is group 4, and the number of electrons that this oxygen has in the molecule, 1, 2, 3, 4, 5, 6, 7. Okay, so that's not good, of course. I'm going to get the same thing happening here. And the carbon is contributing 2 electrons. So, of course, that doesn't work either. And, of course, each oxygen has 1 too many. Carbon has 2 too few. So, of course, we know what's going to happen here because we've done this one before. So it becomes a scenario like this. 2, 4, 6, 8, 10, 12, 14, 16. If I was to do the same thing here, 1, 2, 3, 4, 5, 6. That oxygen's good. This oxygen's going to be similar. And carbon, 1, 2, 3, 4. Good. So that's the structure for CO2. And of course, 1 atom bonded to 2 things. So a possibility here is linear. And that's in fact what this is. It's going to be a linear shape. All right, if we look at the next one, I don't have my sheet, but I think it's, let's see, B, it's a SO3. So if we work that out, sulfur is a group 6. Oxygen is also a group 6. So that's the scenario we're going to be dealing with there. So it's going to give us 6 plus 18, which is 24 valence electrons. And if I join that sulfur up to the 3 oxygens, and then put the extra electrons around those outer oxygens as one of the first steps, 2, 4, 6, 8, and 8 times 3 is 24, so this is what I get. And of course, if I just randomly go around and figure out the formal charges, oxygen and sulfur are all group 6. 1, 2, 3, 4, 5, 6, 7. So of course, yes, that's not going to work. That's okay though. And this sulfur, 1, 2, 3. So you can see what's going to happen here. Each oxygen has 1 too many electrons. The sulfur needs 3 more. So all of these are going to form a double bond. A double bond should make it work. So just redrawing those, that moved over there, so we have this. And now if we figure out the charges here, 1, 2, 3, 4, 5, 6, okay, we're good there. We're going to be good here. We're going to be good here. Oops. 1, 2, 3, 4, 5, 6. Yes, that sulfur is good. And this oxygen is good. And of course, sulfur ends up with more than an octet, but that's okay because the formal charge calculation takes precedent over that central atom having an octet. So that's the right structure. 1 bonded to 3. And if we go back here, oh yes, those oxygens are going to repel each other a little bit. So more accurately, now you could just leave it like this as long as you say that's going to be trigonal planar. So trigonal planar, but if I really wanted to draw it how it actually looks, I would draw it such that these angles are closer to 120 here. Do you have to redraw it? No, because you simply writing trigonal planar implies that you know that the shape looks more like that. So you don't necessarily have to redraw it. You could just simply state that shape. Okay, and the last one we have here, I believe, is carbon tetrachloride. So we have 1 carbon, 4 chlorines. Carbon, of course, is group 4. Chlorine is group 7. So 4 plus 28 is 32 valence electrons. Kind of got ahead of myself there. So draw the extra electrons on the Cl. And let's see what I have here. So we have, and you'll notice that all the time here, we're going to have 8 electrons, 2, 4, 6, 8. 8 times 4 is 32. And yeah, this was on the previous page, wasn't it? Carbon tetrachloride. So we know that this one works because 1, 2, 3, 4, 5, 6, 7. Yes, it's good there. And of course, the carbon, valence of 4, 1, 2, 3, 4. And it has 4, 2. So it's good. And of course, looking back, 1 atom bonded to 4. That's the old tetrahedral shape. Tetrahedral, the shape I really need-dral. Tetrahedral. There we go. Okay, and with the assignment, I asked a couple of questions there. The first part, some qualitative questions. So you should be able to figure that out. I asked about bond angles, and then on the flip side, number 3, you have practice doing this, the drawing, and then stating the resulting shape. So you should be able to do that, and we'll see you again.